Hello everyone, let's talk about the Monte Carlo simulation in this lecture. Instead of a particular analysis technique, the Monte Carlo simulation is more like a way of thinking from a probability perspective. So before today's lecture, let's take a brief review about the concept of probability. We need to figure out two concepts. The first one is event. An event is a desired outcome. It can be any outcome you desire. For instance, if we want to reach $10,000 net profit in the first quarter, then getting the $10,000 net profit will be the event in our analysis. The next important concept is the probability. A probability is a chance of getting a desired outcome. In other words, the chance of getting an event. Suppose we predict that the probability of getting the $10,000 net profit is 20%. Then 20% is the probability of getting the event in our analysis. Now let's use these concepts to do some exercises. First, Joe is tossing a die. He is playing a tossing a die game. What is the probability of getting the two dots on the top side once the die lands on the table? Here we need to figure out the event and its probability. Obviously, the event is to get the two dots on the top side. What is the probability? The probability in this case is simple. It is 1 over 6. We could get 1 dot on the top side, 2 dots on the top side, 3 dots, 4 dots, 5 dots, or 6 dots. Totally, we have 6 possibilities. But in our analysis, we are only interested in getting the 2 dots on the top side. So we have 1 out of 6 possibilities. The probability of our event is 1 over 6. Let's see another example. An analyst is predicting the opening price of a stock tomorrow. Currently, he estimates that there will be 4 possibilities: $92 per share, $93, $94, or $95. For each event, he also estimates the probability. For instance, he predicted that the probability of reaching $92 per share is 10%. The probability of reaching $93 per share is 30%. The probability of reaching $94 per share is 20%. And the probability of the last event, reaching $95 per share, is 40%. Because this analyst has predicted all possible events and their probabilities, we do not need to repeat the analysis again. But there are some interesting key features in this example. First, what is the value of total possibilities of all possible events? If you add 10%, 20%, 30%, and 40% together, the total value is 100%. That means this analyst has considered all possible outcomes for a factor being analyzed. In our case, he has considered all possible opening prices of the stock. In the future, you can do the same. You can estimate all possible events of a factor and estimate the probability of each event. If we draw all possible events and their probabilities on a chart like the one in this slide, we created something called a probability distribution. Remember the key feature of a probability distribution. It shows all possible events of a factor, and the total probabilities should be 100% in a probability distribution. Another interesting key feature of this example is that the analyst only considered $92, $93, $94, or $95. What is the data type of these values? they are discrete data. If we create a probability distribution for discrete events, we call this distribution the discrete probability distribution. What about the continuous data? Can we also create the distribution for continuous data? Yes, we can. Suppose the analyst is predicting the stock price again. This time, he believes that the stock price can be any value between $80 and $100 per share. For instance, it can be $90 per share, or $92.56 per share, and so on. All these values are continuous data. In the future, if we create a probability distribution for continuous data, we call it continuous probability distribution. In this example, the analyst also has a very important assumption. He assumed that the probability of reaching any value between $80 and $100 per share is equal. Now he wants to find out what is the probability of reaching $93.75 per share tomorrow. Before we answer this question, let's draw the probability distribution chart for this example first. We just said that the value of total probabilities in a probability distribution chart should be 100%. In other words, it should be the value of 1. And the analyst assumed that the opening price can be any value between $80 and $100 per share. All possible events in this range have an equal probability of being chosen. Then we can use 1 to divide the length of the range 20 to calculate the probability of each event in this range. In the future, if we have continuous data as the values of all events, and the probabilities of all events are equal, we can draw a probability distribution as the one on this slide. We call this distribution the uniform probability distribution chart. In a uniform probability distribution, the value of total probabilities are still 100%, but because the probabilities of all possible events are equal, then we can use 1 to divide the length of a range to calculate the probability of each event in this range. Obviously, in practice, some events will occur more frequently than others. In those cases, we can create a normal distribution like the one on this slide. When we receive a normal distribution, we should pay attention to 3 factors. First, the area under the bell shape should be 1. In other words, the probability under the bell shape is still 100%. Second, we need to look for the mean of the normal distribution. Usually, it is the value that is marked on the x-axis. The mean will separate the bell shape into half-half. This means the probability for the events that are less than the mean value is 50%. The events that are larger than the mean value is also 50%. This is the function of the mean value. Third, we want to look at the standard deviation value. Usually, it will be given for our analysis. The standard deviation shows how the other events change around the mean value. Some classmates may ask a question. If I'm given the mean and the standard deviation of a normal distribution, how do I calculate the probability of reaching certain value? Let's say in this example, the mean is 15,000 and the standard deviation is 4,500. What is the probability of reaching, let's say, 17,000 products sold? This is how you use the normal distribution to find the probability. First, you want to draw the event on the x-axis. Our desired outcome is 17,000. This value is greater than the mean, so it should be on the right side of the mean value. We draw the 17,000 on the x-axis. And then from the 17,000, we draw a straight line to cut the bell shape into two pieces. Next, we want to look at the left side. We want to find out the size of the area in red. If we can find the size of this area, that will be the probability of reaching 17,000. So the next question is, how do we know the size of this area, the red area? Fortunately, we don't have to calculate by hand. We can use the Excel to find the answer. Let me show you how to use the Excel function. In an empty cell, type in equal sign, and then type in norm.dist, and then the left parenthesis. The first parameter we should give to this function is the desired outcome. In our case, we want to reach 17,000 cells, right? So type in 17,000 and then a comma. Next will be the mean of the normal distribution. It is given. It is 15,000. So type in 15,000 and then another comma. The third parameter should be the standard deviation value. It is 4,500. So type in 4,500 and then another comma. For the last parameter, we choose true and then the right parenthesis. Press enter. You can find the probability of reaching 17,000 product sold is 67%. This is how you use the Excel function norm.dist to calculate the probability of reaching a desired event according to their normal distribution. Some classmates may have another question. If we are given a particular probability, can we find the value corresponding to that probability? Yes, we can. We need to use the norm.inv function to find the value. Let's find a new empty cell and then type in equal sign and then type in norm.inv and then left parenthesis. Norm still represents normal distribution. INV represents inverse. That means we have already known a particular probability. Now we want to find out which event is likely to occur at that probability. Let's say we already know the probability is 45%. We want to find out what is the number of products sold is likely to occur at 45%. We should give three parameters to this norm.inv function. First, the known probability. As we just said, the probability is known, it is 45%, so let's type in 0.45 and then a comma. Next, we want to type in the mean of the normal distribution. It is already known, it is 15,000, so type in 15,000 and then another comma. Next, we want to input the standard deviation value. It is 4,500 and then the right parenthesis. Press enter. You can find out at a 45% probability, the number of products sold is likely to be 14,434. This is how you use the norm.inv function to find out the possible value of an event at a known probability. After the review of the probability concept, we are ready to learn the Monte Carlo simulation. I want to use an example to show everyone the difference between Monte Carlo simulation and the traditional analysis. Let's see the example. The ABC company is developing a new smartphone called KoolCal. The company wants to predict the first year profits of this new phone by considering the following factors. First, the selling price per product. Currently, it is priced at $249 per phone. Next, the managers look at the fixed cost factor. They believe that no matter what the profit will be, if they want to launch this new model, they have to invest at least $1 million as the fixed cost. The fixed costs include the first year administrative cost and advertising cost, and so on. Next, the managers look at the variable cost factors, such as the direct labor cost per product. They use C sub I to represent this unknown factor. The second variable cost is the part cost per product. They use C sub P to represent this unknown factor. The last factor they considered is the first year demand. If they use these factors to predict the total profit of the first year, they can get the calculation equation like the one on this slide. Currently, the analysts of this company are looking at three possible scenarios: the base scenario, the best scenario, and the worst scenario. In each scenario, they estimated the values of the unknown factors. For instance, in the base scenario, the analysts estimate that the direct labor cost per smartphone is $45. The part cost per smartphone is $90. And the first year demand is 15,000 units. If they put all this estimated value in the total profit equation, the first year total profit could be $710,000 in this base scenario. In the best scenario, the analysts believe that the cost will be lower, but the demand is higher. For instance, in the best scenario, they estimate the direct labor cost per smartphone is only $43. The part cost per smartphone is $80, but the demand will be 30,000 units. If they put these values into the total profit calculation, they get that the first year total profit in the best scenario could be $2.7 million. They do the same for the worst scenario. The analysts believe that the cost factors will be higher and there is no demand for the smartphone in the first year. In the worst case, the company will basically suffer a $1 million loss. Analyzing the market from three different scenarios seems like a very reasonable strategy. But can you find some weaknesses of this strategy? There are two weaknesses of the current analysis strategy. First, the analysts only look at three scenarios. They basically ignored some other scenarios. Second, the analysts only look at the events in different scenarios. For instance, they estimated how much will be for the direct labor cost in the base scenario, best scenario, and the worst scenario. However, they really didn't look at the probability of this event. They didn't look at the probability of that particular direct labor cost to occur in different scenarios. The ignorance of the probability makes the current analysis very subjective. These are the weaknesses of the current analysis strategy. So what should we do? How can we address these issues? We use the Monte Carlo simulation as a solution to address all of these issues. The Monte Carlo simulation is a new perspective of performing the data analysis that involves unknown factors. When we use this method, we usually will go through 5 major steps. First, before the data analysis, we want to find out all unknown factors in the question. More important, we want to find out each unknown factor's probability distribution. In our case, we have 3 unknown factors. They are the direct labor cost per smartphone, the part cost per smartphone, and the first year demand of the new phone. After we identify these 3 unknown factors, we want to do a little more research about each factor and find out the probability distribution for each unknown factor. Currently, the analyst in the ABC company hasn't found out the probability distribution for the direct labor cost, part cost, and the first year demand. So if we want to use the Monte Carlo simulation to predict the first year total profit that is most likely to occur, we have to find out the probability distribution for these three unknown factors before the data analysis. Second step, we want to expand the possible scenarios from 3 scenarios to a large number of scenarios. In our current analysis, we only considered 3 possible scenarios: the base scenario, the best scenario, and the worst scenario. But when we use the Monte Carlo simulation, we want to expand the scenarios to a larger number. Let's say 1,000 scenarios, 2,000 scenarios, or even more. The larger the number of scenarios is, the more accurate the predicted profit will be. Why? Because when we consider more different scenarios, we basically predict the profit from more possibilities. Therefore, the predicted profit will be more accurate. Now let's talk about the third step. In each scenario, for each unknown factor, we want to let the analysis software generate a random number that is between 0 and 1. We use the Greek letter delta to denote each random number. And then we can move to the next step, the fourth step. We want to bring each random number delta to each unknown factor's probability distribution and find out what the value is likely to be corresponding to the random number in each unknown factor's probability distribution. The set of chosen values for all unknown factors is called a trial. After the first trial in the first scenario, we can repeat the same process above to get other trials in other scenarios. We consider all trials when we predict the profit, so that we can show the probability distribution of the profit. Some classmates may have a question. Why do we want the software to generate a random number for each unknown factor in each scenario? What is the benefit of using the Monte Carlo simulation? Keep in mind that the key feature of the random number delta is that it is between 0 and 1. When we bring each delta to each unknown factor's probability distribution, basically we want to use delta value as a pseudo probability and find out what the value is likely to be for that unknown factor in that particular scenario. When we have a large number of different scenarios, we can then simulate the unknown market, the changing future in our analysis. Let's see how we can use the Monte Carlo simulation in our question. First, the analysts need to figure out the distribution, the probability distribution for each unknown factor in the analysis. We have 3 unknown factors, right? The direct labor cost per smartphone, the part cost per smartphone, and the first year demand. We need to find out each factor's probability distribution. After a little more research, the analysts find that instead of 3 possible values, the direct labor cost can actually have 5 possible values. They are $43, $44, $45, $46, or $47 per smartphone. And these values follow the discrete probability distribution. This slide shows the possibility of reaching different direct labor costs at a different probability. When we perform the Monte Carlo simulation analysis in the future, when the software generates a random number delta, we bring the random number delta into this distribution chart and use it as a pseudo probability, and then find out what is the value is likely to be for the direct labor cost in that scenario. Let's say in the first scenario, the random number is 0.4. We look up the probability distribution chart and find out when the probability is 0.4, the value is likely to be $45 per smartphone. And then we use $45 as a value for the direct labor cost in the first scenario. The analyst then took a look at the part cost per smartphone factor. He found that part cost is following a uniform probability distribution. There could be an equal chance for the part cost to be any value between $80 and $100 per smartphone. He then took a look at the first year demand. He found that the first year demand follows a normal distribution. The mean is 15,000 and the standard deviation is 4,500. After we figured out the probability distributions of all unknown factors, we are ready to start the Monte Carlo simulation process. Suppose we want to create 1,000 scenarios in our analysis. Let's see how we process the first scenario. In the first scenario, we want the software to generate one random number for the direct labor cost per smartphone, another random number for the part cost per smartphone, and a third random number for the first year demand. And then using these random numbers, we look up the possible values for the direct labor cost, part cost, and the first year demand according to their probability distributions. Suppose in the first scenario, we get 0.4 as the random number for the direct labor cost, 0.3 as the random number for the part cost, 0.6 as the random number for the demand factor. When we look up the probability distribution of the direct labor cost, we find that $45 is the most likely value for the direct labor cost if the probability is 0.4. So in the first scenario, we identify that the value for the direct labor cost should be $45. For the first year demand factor, we can use the norm.inv function we learned earlier in this lecture to find the corresponding value if a probability is known in a normal distribution. In this case, the random number for the first year demand is 0.6. We use this value as a pseudo probability and then find out the corresponding value to the 0.6 probability is 16,141. This will be the estimated value of the first year demand in the first scenario. It seems that there is only one unknown factor left in the first scenario, that is the part cost per smartphone. We have known that the part cost per smartphone has a random number 0.3. We also know that part cost follows the uniform probability distribution. If we have known these two information, we can use this equation on this slide to calculate the corresponding value for the part cost per smartphone. We got the corresponding value as 86. So in the first scenario, the estimated part cost per smartphone should be $86. If we put all the estimated values into the profit calculation equation, we predicted that the first year profit could be $904,000 in the first scenario. We can repeat the same process in other 999 scenarios and find out the projected profits in other scenarios as well. On eCollege, I uploaded an analyst guide to show everyone how to implement a Monte Carlo simulation in a dataset. After today's lecture, please take a look at the guide and implement the simulation in the dataset.